Hello，Hello，这应该怎么测试一下？放个歌。
对，我想看一下那个屏幕上，因为这边 Mm. Yeah, no, I should use this one for the adapt. Yeah. Mhm. Mm. Is it the asking camera?
No, so if you press on the camera, not on the camera video, it says video.
Mm.
Yeah. So that's saying that is yours. Yeah. So we press again. It's gonna be bio. No, not bio.
Maybe not this one. It's not fine.
Unplug it and plug it again.
Mhm. We should okay, so
Just go there, turn the camera off.
um, Destroying.
Recording in progress.
Still not showing. I have no idea where this image come from because it doesn't, it seems like it is from this one here. 怎么？就是怎么那个找不到这个？我看看。我这里是进了的，可是这个外一个的那个 speaker， 这个电脑的 speaker， 对，是 mute speaker。
Yeah. Yeah. It says mirror my video. I think not that one. That's your fault, isn't it?
Yeah, no, why?
Oh, check it.
Oh, yeah.
Trying to see which color.
Yeah, I also have no idea really.
没电了吗？
There's another.
This is
Let's start with
this
one here.
here.
Keep it there, please. And turn the video off. Keep it off this time. Then the video off. So get the video off, then press the brake.
Close this one.
And okay, let's go ahead. Check.
No.
That is only one camera.
No, it's good to restart your PC. Sorry for that, but we're trying to. It could be this adapter, so if you restart, then tell us. If it doesn't work, we'll get another adapter.
Sure.
Oh, before you restart, have you closed the?
It's
Find another adapter. 这是在那个
对对对。
Let's give it a restart.
HDMI 是吧
对对 USB
It's gonna be USB-C.
？USB-C HDMI。
You have another C USB there?
No, so there are
Just.
two, yeah. speaker 加入这个 webinar link 吗？还是说
他
吧？
们如果要是没有来，就得用。
那他如果来了是拿，就是把那个文件给。
进那个 link 里。之前我电脑都是做那个 backup 从，就还是第一次接这个设备。OK，
那个应该是 adapter 的问题，因为我这里还是只有我电脑自己。嗯，这确实也不是不行，用这个。嗯。然后是你和所有 presenter 加入这个链接是吗？啊，是，稍等，我找一下。嗯，这个是如何发给别人？
不用发给我，直接在这里。他们最后present的时候都直接在这里打开。
OK。
他那个 Google Drive 的 link。
哦，Google Drive 的。
对。
这个是啥呀？
你没有收到他们所有的 slides 都要上传到一个 Google Drive 上。
哦，这个呀，OK，我知道。嗯。看一下。对，这应该是第四个。
可能谁在会下来着？
他们有这个会议的 link 吗？
应该是有的。
那我们都上不了呼法，都只能纯靠那个 Outlook 里面的那个就翻那些 meeting 去。
No, still couldn't connect to that camera. But I guess it should be fine. That should be okay. 我们就先这样。
好的，这些需要下载吗？还是 OK？
是就这样。
好的，好的。嗯，
公司弄的东西得关了。
是的，我正在关。是的，我正在关，不过还好，我昨天关了一下，就想到了这种情况。
是命的。
对的，是的。
Yeah, I guess just use laptop camera to be fine. That's fine. Just use laptop camera. Yeah.
Yeah.
It's not working. It should be fine.
If you plug it, did you try to plug it straight
Now
away?
we are going to present very soon.
Just to try.
Let's give it a
Well,
go.
I'm not.
No. 这是你的哈，你得 log off WiFi，要不然它永远会 log 到你的。
哦，
That's
这
it.
这些
Okay, that's it. The bio. Bio 500. I will put the charger. Should have charging there. Will you check please? No, let's go back to the camera. The camera is there.
Yeah, why?
So it's bio 500. And then just the one.
Yeah,
it's off.
Okay. All right, so the
No,
charging,
yeah.
the charger is okay?
Yes,
Yes.
everything is fine.
Okay, so you gotta keep that back up in case.
插上了，插上了。哎，但是我好怕这样把主板烧了呀。我之前主板
不会的
这样被烧，就是
没事
通过扩展无冲。
一般都不会。
是那个他要直接插是吗？
对，算就这样吧，2个小时，电1个半小时吧，不会怎么样。
我们接的电源线比这多多。那你是 Air 对吧？
对，对，就是当时买的时候，那个 Pro 多接口的那个还没出。
那就 OK，不能那个 one panelist。OK， 这样应该没问题。你看一下，咱们得 share，因为你这只 share 了，如果他们 present 但是看不到的，所以我们得 share desktop。
OK
好吧，基本没啥了，不用担心。
行 OK。是前2天没用，是吗？
这
看 presenter view
不好弄的，present view，不用管这个，没事儿，不用担心，因为这个是在线的，我不知道他们能不能看到 present view。
哦，行行。
要什么词？OK，好，
这可以用 present view 就这个。
这我们试，因为这个是在线的，可能我直接给你改成这种 view 还不太行。如果你看啊，这是 present view，你看点上，是不是也都能看到啊？
是苹果电脑吗？
对，苹果。
还有设置多屏模式吗？
我看一下模式，如果要是多屏模式按钮是行的。哦，是按。OK，这个还不太行，OK， test test. All good. Thank you. Just let me double check whether online users can hear us. Seems so good. Online attendees. Okay. So welcome to today's session, Web for Good Session 2. Today we will have 5 speakers. And then for each speaker, you would have 20 minutes for presentation, 10 minutes for Q&A. Welcome to this session. Then today we start with self-played about RM-based recommendation system. So let's welcome our first speaker.
And okay. Good morning, everyone. And I'm Chen Ruijun from University of Science and Technology of China. And today I'm glad to be here to give a presentation of our work as self-play to deposit LLM-based recommendation. And in this work, we aim to focus on the best issue, the LLM-based recommendation, and use a self-play strategy to just the problem. And
Okay.
and
这个还不太行，这个
and
，OK，
and And the presentation will be divided into three parts. No. Sorry. Okay. And Okay, can I start from here? Okay, and let's start from the background and motivation of our study. So recently, there's a growing trend in LLM-based recommendations, and we use its strong contextual understanding and powerful reasoning ability to help the recommended system in some typical scenarios like co-star recommendation and like conversational recommendations. So the prevailing methodology for using the LM for recommendation systems include transforming the recommendation data into the language prompt and then generating the prediction through the LM. And here's a Oh, I don't know what happens with the PPT. Okay, and now the two main methods for fine-tuning LM for recommendation mainly include supervised fine-tuning and direct preference optimization. And in SFT, we direct train the LM with user history and target items through the language modeling laws. But this ignores the negative samples, which are essential in recommendation. So researchers adopt DPO using pairwise ranking laws to better align LLMs. And however, our study reveals both methods introduce significant bias. And let's begin with some experimental findings. And we have identified two biases in LLM-based recommendation systems. The first one is token level bias, while the second one is item level bias. And token level bias means when we use the LM for recommendation, the LM will favor movies titles with some frequent tokens. For example, it may prefer the token the, and the item level bias, in contrast, may focus exclusively in some similar movies. For example, it may focus exclusively in some films from the Batman series. So we would like to ask, how do SFT and DPO introduce this bias? And our work uncovers the underlying mechanism, KL divergence. I'm really sorry. And so now. Okay. And now let's briefly review the KL divergence. So how does KL divergence conform these two impacts on LLM-based recommendation systems? And let's suppose the p-axis is the target distribution and the q-axis is the learned distribution. And as the KL divergence is asymmetric, when we use these two different KL divergence, there will be two different influence on the alignment process. So when we use the forward KL divergence, if the target distribution has two modes, for example, and when we use the forward KL, the learning distribution will tend to cover all the modes. Or in other words, we can say there is a mask covering resource in the KL divergence. And in contrast, when we use reverse KL, the learning distribution will tend to capture only one mode, which is often described as the mode-seeking behavior. And here's an intuitive illustration of the two modes. So let's come back to the LLM-based recommender systems. And we first discuss the impacts of the SFT approach of the LLM-based recommendation. So the SFT-based method formulates the recommendation data as the language prompts, then train the model with the language modeling laws. And from here, we can see these laws can be rewritten in the form of a KL divergence. Specifically, we can observe that the SFT objectives is equivalent to the forward KL divergence between the data distribution and the model's outputs. So as a result, the SFT will suffer from a mask covering resource. And besides, as we discussed earlier, there is an inherent token level bias, or for example, the model will prefer some tokens in the title, like they prefer the, and so these two factors, the mask covering resource and the token level bias, are the main types of bias in the SFT-based methods. Okay, this was fine. And so after SFT methods, so we are going to introduce about DPO method and how the bias is generated. And here's a loss function from the DPO loss, and also it is a closed form solution to the RLHF objective, which is at this line. So we can see that it can be rewritten as a reverse KL from the pi theta or the model parameters and the pi star, where pi star is a reward function, is a distribution, and it is related to the reward function and the model's reference model. So from here, we can see that the DPO or the RLHF can be written as a reverse KL. Okay, so in addition, unlike some natural language processing tasks, and in recommendation scenarios, we can write our positive samples and negative samples are dividedly sampled. So we have a strong conclusion that we can write the optimal policy of the DPO loss in this form. In this form, and so from here we can see that while PD represents the conditional probability item in the data set, and the QD represents the conditional probability of item in the negative samples. So we can see that DPO tends to favor items with higher PD or those who are more popular in the data sets. And moreover, we have the conclusion that when the QD is uniform, or we use the random sample to sample our negative samples. And as the beta reaches 0, the optimal policy converges to only recommending only the most popular items. And so far, we have analyzed the theoretical reasons behind the bias introduced by DPO. So we can find that the DPO tends to recommend popular items. Or in other words, it focuses on the peaks of the dataset distribution. And in addition, we can observe in practice that DPO do not effectively adjust the inherent token level bias. And then we illustrate these two factors in this fig. And also we do an experiment on co-star recommendation to further illustrate the problem. And here's the recommendation results, and the group 0 means the least popular items, and the group 4 means the most popular group. So we can see that after DPO training, DPO ends up recommending only the most popular items, which also further confirms our conclusion. And in the next part, I will introduce how we use the self-play strategy to address the bias issues. Self-play was originally introduced in reinforcement learning when it refers to a process in which a model iteratively improves itself by playing against itself, its outputs. So a well-known example is its use in games like Go, for instance, AlphaGo and AlphaGo Zero. And in the LM era, self-play fine-tuning is a new paradigm that emerged as a new training strategy. Its definition that the LM refines its capability by playing against instance or itself. So, and its advantage is it can remove the need of acquiring additional human analytic data. So, while the self-play fine-tuning is typically used for improved model performance, we would like to ask, how does self-play fine-tuning works for debiasing? To answer this, we focus what happens when we combine the self-play negative sampling and the DPO. When the model's own outputs are used as negative samples, this process can be interpreted as implicitly with the DPO loss with this term, and this term we can say that it implicitly with the DPO loss by the model's output probability. So as a result, items that appears more frequently in the model's outputs will receive more suppression or during the training. So if we suppress those popular items, we can achieve a more balanced recommendation, and this is the key advantage of self-play fine-tuning for debiasing. So, and these are two advantages. Okay, so this brings us. It skips too many pages. I click once. So this brings us to our proposed training framework, SPRAC. SPRAC consists of multiple training iterations, and each iteration involves 3 key steps. And first, we construct our data through the pairwise training data. And the negative samples is sampled from the model's predicted results, and the positive items is from the offline ground truth. Then we perform SFT fine-tuning on positive items only, and this step is to maintaining the recommendation accuracy. After that, we perform the DPO aligned with self-generated, and this is our SP training pipeline, not very complex but highly effective. And as shown in the figure on the right, we are able to dynamically suppress the peaks or suppress the bias during the training, and therefore achieve debiasing. And next, I will introduce about our experiments. And I will briefly introduce the metrics. As for the recommendation accuracy, we use the NDCG and HR and the hit rate, which are widely used in the LLM-based recommendation system. And as for the recommendation diversity, we use 2 intuitive metrics: the diversity ratio and the OR ratio, or you can understand it as the over-recommendation ratio, which the diversity ratio means the proportion of the unique recommendation results, and the over-recommendation means the proportion of the most popular items. And as the fairness, we use the mean group unfairness, which is the category level discrepancy between the LN's output and the use history. So let's move on to the question one, the overall conformance comparison. From the table, we can observe that the SFT-based method suffered from severe biases and the overexposure of popular items. Both the fairness metrics and the diversity metrics are notably low. And for DPO-based methods, SPPO and the DMPO, which use the random sample negatives, improve DPO by use, and they adopt the multiple negative samples to improve the performance. However, they still fail to adjust the fairness problem, and the Rose PO use a semantic negative sampling. It shows some effectiveness on some datasets like GREE and CDE datasets, but perform poorly on the other. So we can say that it relies on the semantic characteristics of the dataset. And in contrast, our method, Str-GCL, achieves the best fairness and diversity metrics, offering a universal solution across different datasets. And okay, yeah. Oh, I don't display it, I think that's right. So let's move on to the research question one. We also conduct some ablation study to demonstrate the effectiveness of our three components. When we remove the SFT stage, we observe that the model places too much emphasis on improving the accuracy. Oh, too many emphasis on improving the fairness, yes, without SFT. And so although the recommendation results become more balanced, the accuracy significant jobs. So, and when we remove the DPO stage, this corresponds to an additional SFT stage training. And in this case, we find that relying solely on SFT does not address the fairness issue in the model. And finally, when we remove the self-play negative sampling, or when we use the random negative sampling, and the model still failed to resolve the fairness problem. And this concludes the ablation study parts. And finally, we conduct some experiments to assess the impact of negative samples. We examine two factors. The first one is the random sampling ratio, and which means we mix some random negative samples into our training process, and we observe a drop in both fairness and diversity, which underscores the effectiveness of our self-play negative samplings. And in contrast, increasing the negative sample size also leads to higher diversity and diversity, but the accuracy remains steady. This suggests that our self-play approach can also be combined with existing multi-negative sample DPO methods. For example, we can combine it with the SDPO to further debug the large language model-based systems. Okay, and that concludes the experiment parts. Yeah, it's not displayed correctly. Okay, maybe I can adjust this. Oh, I should use the PDF. Okay, and here's the brief introduction and summary of our work. And we are the first to establish the theoretical link and the preference alignment in large language model-based recommended systems. And also, we pioneered the self-play strategy for debiasing the large language model-based recommended system. And our future direction may include the long-term alignment. We want to extend the recommended system to sequential recommendation. As you know, now the large language model-based recommended systems only recommend one item once, and so yeah, we may want to extend it to sequential recommendation. And the second direction may be the process level rewards. We can replace the token level optimization for example, we can use the process level rewards or sequence level rewards for sustainable engagement. And okay, and thank you. And thank you for your attention. I look forward to any questions.
Yeah, thank you very much.
Very sorry. I don't know what happens for this.
So from audience, do we have any questions? Okay, so maybe one quick question. Can you please explain, like, for example, for example, you try to debug
Okay.
a recommendation.
Yeah, you mean how do I devise the system?
Yes.
Okay, thank you. Yes, maybe that I don't explain much about this. So we summary the two kinds of bias in figures like this, or we find that the bias in SFT methods and the DPO methods, we can say that the bias is from these peaks. Yeah, both the DPO and SFT may generate something like peaks, or we can say the large language model-based recommender systems may overemphasize some popular items. So our aim is to adaptively suppress the peaks. So we put these peaks on the next samples in the DPO and adaptively suppress them. So our final results may become like this. Like we suppress those peaks and or suppress those popular items, and we can say the bias suppress in cell play. And that's how we achieve a balanced recommendation results.
Thank you very much. The time limit.
Yeah.
We probably need to have a discussion offline, and then let's thank our speaker again. Thank you. And then our next talk is Auslan Web, a scalable web-based Australian Sign Language communication system for deaf and hearing individuals. Let me see. Okay. Because our speaker is not here, so we will display the video. Let me see.
Our research title Auslan Web, a scalable web-based output.
But let me make sure the author is online. Can I double check? I think we have, yes. So the author is online. Can I ask whether we can put the author in the panelist? So in that case, offline, the person answer the questions. But without further ado, we just display this recording first. Would you please?
The University of Queensland, FG-CIBGC, and Australian National University. Let's start by understanding the significance of our research. Here I present some data related to the deaf individuals. Hearing loss is becoming a bigger issue both worldwide and in Australia. Globally, the World Health Organization reports that over 5% of world's population suffer hard of hearing. By 2050, this number is expected to rise to 700 million, or 1 in 6 people. In Australia, as of 2015, 1 in 6 Australians suffered. Means that
Sorry, let me just let's try this one.
significant limitations. Each sign language has its own vocabulary and grammatical rules. For example, we look at the outline, ASL and ESL signs, the word pair, and each language uses a different sign. And the second limitation is lower resource and language processing. Lower resource means that there are limited samples available for training. Here's an example. Phoenix is a commonly used data set for sign language translation task. We must see is a subset of machine translation dataset. The must see dataset is 30 times larger than Phoenix compared to another tasks. All sign language processing tasks belongs to the low resource setting. Low resource tasks will have the following issues. First, one is overfitting risk. Since the limited number of samples, models may overfit to their few samples and cannot generalize to unseen data. And the second is missing language diversity and complexity. The lower resource language often have learning grammatical structures and vocabularies. The lack of enough data makes it challenging for models to capture this complexity. Outstressed language, known as Auslan, logs robust to accurate translation. That's addressing this communication barrier is not just necessary. It is important for improving social inclusion and equal opportunities. In response to these issues, our research focuses on developing an accessible, scalable, and effective web-based communication system on the web. Our main objectives include bridging the communication gap between enabling accurate bidirectional translation between Auslan and English. Additionally, we aim to mitigate data dependency issues in carrier sign language translation systems by integrating linguistic insights with advanced artificial intelligence methods, particularly large language models. Before we show the functions of Auslan Web, it is important to first introduce the word level Auslan data set. That is we previously focused. It contains over 3,200 commonly used isolated signs, about 300,000 video samples, features 73 different signers, and covers multiple data types like RGB, depth, and post information. Here are some samples from our dataset. Our signers exhibit great diversity in both age and race. Compared to our existing isolated sign language recognition datasets, ours is the largest and includes both multi-view and depth information. And to evaluate the performance of isolated sign language system under real-world scenario, we provide a diverse test set with 4 distinct subsets, including studio set, each seems with the data. In the wild set, we captured the studio without green background. We extract signer from the video and synthesis indoor and outdoor backgrounds in the synthetic set. The KT set simulated potential recording time mistakes in real-world scenario by randomly adjusting video segments through removal or alternating playback speed. Now I will introduce our proposed Auslan Web. It is specifically designed as a web-based platform to ensure broader accessibility and ease of use. It's supposed to mean translation functionalities. Firstly, translating isolated signs, which involves identifying and mapping individual signs or gestures to their equivalent words or phrase. Second, translating successive signs or sequence of gestures into coherent long-form spoken language sentence. These two capabilities ensure comprehensive support for both short, simple communication and complex conversational exchanges. Next, let me introduce our core knowledges within Outline Web. The first one is Outline Dictionary. To achieve effective retrieval, we employ the semantic matching strategy powered by multilingual embeddings generated through the MBAR model. When users query a specific word or phrase, our system calculates cosine similarity between the query's embedding and all close embeddings in the database. This semantic approach ensures robust retrieval even when directly matchings are unavailable. Importantly, our dictionary can handle out of vocabulary. If an exact matching isn't found, the system intelligently scares the close semantic alternatives, and if necessary, provides finger spelling representations. This ensures the meaningful results are always delivered. Significantly enhances the user experience, language learning, and daily communication accessibility. The isolated sign language recognition model is central to accuracy of Outline Web. We integrate great data modalities, RGB video, capture visual appearance. Depth sensors provide spectral detail and close estimation technology to track motion of hands and body. Each modality undergoes pre-processing and is analyzed by the state-of-art models. By combination outputs through logist ensemble, we significantly enhance recognition accuracy. The multi-mode approach allows our system to reliably perform across varying real-world conditions, effectively handling different view angles, lightning scenarios, and complex backgrounds. As shown in this experiment results table, our isolated sign recognition shows clear accuracy benefits from multi-mode integration, particularly when using the RGBD data. Before we talk about the translation capabilities of our system, it is important to clarify the difference between the three main types of sign language formats: isolated, continuous, and successive sign language. Successive sign language, which is the format our system focuses on, offers a balanced middle ground. It contains sequentials of flows, where each sign has a clear end, just like isolated sign language. As these signs appear in the natural order. This distinction is important because it allows us to build a more scalable and effective translation while leveraging current isolated sign language recognition research and data sets. To translation. Three-step outline. Initially, we normalize the English inputs and address the grammar and punctuation errors. We then extract the core part of the sentence, like the subject, verb, and any key contents such as time or place. After that, we'll apply the Outline grammar rules to rearrange these elements into the right sign order. At this stage, we also use prompt engineering with a large language model to help decide the most natural and grammatically correct flow sequence. Next, the system retrieves the corresponding Outline glosses using our semantic dictionary matching approach. If certain terms are not found, we use a finger spelling as a reliable fallback. That's an English query like, could you tell me the weather tomorrow? The translations smoothly into the Outline gloss moral wiser words. Conversely, our Auslan to English translation apply involves accurately recognizing gloss from the sign video and analyzing their semantic flexibility. Each gloss may have represent several English meanings. Hence, complex word integration is crucial. Leveraging powerful large language models, our system generates translations that are semantically correct and grammatically accurate. This process handles ambiguity, producing sentences that closely matching the intent meaning. For example, the Auslan gloss moral, weather cloudy, translates frequently into the English sentence. The weather will be cloudy tomorrow, highlighting our system's capability in semantic reconstruction. To understand how well our system works, we run both technical tests and user studies. For successive sign language translation, both from Auslan to English and another way around, the results were very positive. On average, both staff users and Auslan experts gave the score about 4 out of 5. They especially like how accurate, smooth, and easy to understand the translation were. Importantly, user feedback highlighted significant improvements in everyday communication and social integration, validating our approach and its real-world applicability. Finally, there are several existing directions we plan to explore to make Auslan Web even better. First, we want to support different regional dialects and variation in Auslan so that the system can work well for a wider range of users. We are also looking to real-time translation, which would make conversation smoother and more natural in live settings. On top of that, we will keep working to improve the system's accuracy and reliability by using better recognition methods and more diverse training data. All of these improvements will help Auslan Web become even more useful application. Finally, our demo video are public available online and code will release for further explanation and use. I appreciate your attention and welcome your questions, insights, or suggestions. Thank you for listening.
Okay, thank you very much for the presenter. So do we have any questions from the audience? Maybe I can ask a question. So let me see whether the author is online. Yep, the author is online. So for your case, yes. So for your case, you mainly focus on like, for example, try to concatenate also isolated glosses. So I guess for your case, you simply concatenate all the Auslan glosses. So whether you did some subjective like evaluation with the deaf users or some people, they have experienced hard hearing, and then what's their feedback? And also for linguistic side, how can you express some classifiers and registers? Thank you.
Thank you for your question. Yeah, can you hear me? I'll double check. Yeah. For evaluation of our system, because there is no large scale sign language translation data.
Can you speak a little bit loud?
Okay, sorry. Thank you for your question. And to evaluation our system, because for now there are not large scale sign language translation data set for outline. So in this paper, we are focused on to use user study, and then maybe for the further evaluation, we want to create more large data set about like the gloss and natural language pairs, and to evaluate the performance of our system. I think it should be more correctly to evaluate our system.
Okay. Thank you. So we'll move to our next talk. Thank you very much.
Thank you.
Let's thank the author again. Thank you. So our next talk is detecting linguistic bias in government documents using large language model. So may I ask whether is this one? Thank you. Just make sure. Hopefully it will be.
Yeah, thank you. So can you hear me from the back script? Yeah, today I'm going to introduce our work detecting linguistic bias in government documents using large language models. It's a joint work with Milena and Flores. This is yeah, this was based on Milena's thesis, a master thesis while she was doing an internship at the Minister of Education, Culture, and Science of the Netherlands. So what is linguistic bias? Linguistic bias is defined as a systematic asymmetry in word choice as a function of social category to which the target belongs to. Okay. So in the table, in the first sentence, you can see that if we the term handicapped is considered as a bias because we use this term to label a group of people who are disabled. And usually linguistic bias is hidden and often unattended. Therefore, it makes it difficult to detect such bias and is often inconsistent. Here we have the list of a bias detection data set. As you can see, that most data set are focused on English, and the data source is majority come from Wikipedia, news, and social media. In our work, particularly interested in government text. In our work, particularly. Let's try again. I hope it works now. Yeah. So in our work, particularly interested in government text because government texts are super important in our daily life. We use it to shape laws, policies, and this is how citizens understand their rights and responsibility. Those texts are supposed to be neutral and objective. However, because the documents are written by humans, therefore bias is often unavoidable. in reality, those bias as is hidden and usually exists in language for decades. Therefore, if it contains a bias in document published by the government, it will enforce stereotypes and discriminate a certain group of people. And in terms of policy making, it will further disadvantage a certain group of people. Therefore, we would like, it potentially will also further impact the public trust as those documents are considered authoritative. Therefore, it's very important for us to make sure that a fair and inclusive communication in government documents. In our work, we provide a Dutch government data set for bias detection, and we also further fine-tune Dutch bird models based on existing fine-tuned bird models for bias detection tasks. And we also propose a new evaluation and analysis. We hope that our work and those benchmark and fine-tuned models can ensure fair governance and policy making. Our data source is come from a Dutch House of Representatives. You can find all the documents on this website. These documents are formal government communications, including ministerial notes, memoranda, and reports, and also all related documents that associate with them. On the left-hand side, you can see the data creation pipeline. It mainly consists of two phases. The first phase is a data collection. It is an automated process as highlighted in blue. So we start with 120 keywords that are identified by a group of Dutch linguists that potentially can identify bias. And then we use these keywords to match a sentence in the government documents. And in the end, we further normalize it, and we received 12,000 sentences. The second phase is a data annotation phase. Those are manual process. We have a group of 14 experts who are native Dutch speakers. They are working for the governments, and they have expertise in discrimination, racism, and bias. In order to streamline the annotation process, we first organize those keywords into 3 distinct groups. Prohibited, this is the group of terms that we should try to avoid unless we just quote them. The second group is called conditionally biased. This group contains the terms that may contain bias, depends on how we use it. For example, Christian. The third group contains the terms that are context sensitive. Those terms are neutral as it is, but it might contain bias, depends on the context. For example, in the table, you can see the influx. Influx itself is neutral. However, if we said a large influx of refugees, it will contain the bias. The whole annotation process will contain of a discussion, chaining, and refining process. We use at least a definition to define whether a sentence contains bias or not. We say a sentence contains a bias if it satisfies one of the following conditions. The sentence contains a term from the prohibited category, or the sentence contains bias such as the stereotyping, exclusion, power imbalance, or prejudice. And those bias is directly towards a specific group. Here we have, in the end, we get about 3,600 annotated sentences. Among them, 25% sentences are biased. On the right-hand side, you can see an overview of the occurrence of bias terms by category. The top 2 highest occurrence category, art education, and migration. The models we consider in our work are this of a fine-tuned models, such as the Bertrand Robert Sentence-Berg, DAL-CBERT, and we also consider generative large language models such as GPT 3.5 for all meaning. In order to evaluate a model generalization by chaining, we use two different settings. One is in domain setting. We use it to measure performance when bias types have already seen during the training process. The second one is out of domain regime. We use it to test the model's performance when it comes with unseen bias expression. Here is the result. On the right-hand side, you can see a table of F1 text scores of all the models. As you can see, that in domain setting, a fine-tuned budget model has the highest performance. And of course, all fine-tuned BERT models in domain setting, in our domain settings, overperform in domain settings is better than out of domain settings. And in terms of out of domain settings, GPT 3.5 has the highest performance. Additionally, we consider resampling strategies in order to moderate class imbalance, because in our data set, only 25% sentences are labeled as a bias. We use three different strategies. The first one is oversampling strategies. We duplicate bias sentence to increase visibility during training. The second one is undersampling strategy. We randomly remove a portion of a non-bias sentence in order to highlight the bias sentence. The third one is a balanced resampling. That is a combined strategy over and undersampling strategy to increase to create a 50-50 class distribution. Here is the result that you can see in the table on the right-hand side. Oversampling strategies has the best performance in both in domain and out of domain settings. And in terms of oversampling strategy, it slightly improves out of domain performance over none or balanced sampling strategy. As a conclusion, we have introduced a Dutch government data set for bias detection. Those data sets are annotated by the domain experts, and we also provide fine-tuned models to advance fairness in government communication. As a limitation, our approach currently relies on predefined keywords, and the government documents need to be publicly available. And currently, we focus on the Dutch context. However, people can use similar pipeline strategy to extract documents in other countries. As a future work, we would like to further expand data size to include more underrepresented keywords, and also to explore pairwise formats to improve generalization. We would also like to enhance annotation reliability by further refining bias category, and also involve more annotators to create a more refined data set. In the end, I would like to thank the great support we have received from the Dutch Minister of Education, Culture and Science of the Netherlands, and also the Ministry of the Interior and Kingdom Relations. And we also would like to thank all the annotators who contribute to our data sets. Thank you very much.
Thank you very much for the talk. Very interesting topic. So, okay, we have a question.
Thank you. Thanks. Really enjoyed your presentation. Very interesting work. I had a question about your data annotation strategy.
Yeah.
You said you had two parts to the process, where in part 2, there's a bit of a feedback coming in from the sentences that have been labeled to choose the next set of sentences. Can you please elaborate on that? I'm referring to the arrow from labeled instances 3632 going back into sample. The one at the bottom?
You mean this one? Or?
No, yeah, that one, that's right. So how do you select, based on the labeled instances, how do you select the new set of sentences that you want to be labeled?
So I think here maybe it's a little bit, it's not really clear. So basically the idea is, maybe I have this in, so if you can see, it's basically the annotation process is a loop feedback. So we start with the training section, and then we have the pre-test, people start to annotate the sentence. And then we have a further discussion that, okay, is like the current annotation guideline clear enough? And then we further refine it. And then we educate to the next section. So the whole annotation is kind of a loop feedback. I think maybe it's a bit misunderstanding in the previous figure.
Yeah, can I go first? Thank you so much for the presentation. I thought it was very nice. I'm from Holland myself, so it's always interesting to see work being done in the Netherlands. I had a question about the found bias. So in the sentences that were labeled as bias, did you see any difference in where the most bias occurred? So was it mostly in the public debates that you saw, or was it more in the in specific governments or on specific topics, for example, or did you not do such an analysis yet?
So I think we have not figured out that. Here we only shows the category by here on the right hand side. We're more focused on whether it's a culture, whether it's comes from within the education or gender, etc. I think at the moment, we mainly focus on treating all the documents as the same, but maybe later we will further, if it becomes interesting, then it's definitely, it would be our next step to further distinguish, see, okay, what kind of documents may contain more bias than others.
Based on the numbers of from experiments which you showed, somehow results are not really good, right?
You mean
let's say this, yeah, balanced.
you mean, yeah, something, yes.
This balanced 0.4. This is not far from random, actually, right?
It's definitely better than the random because
it's slightly better, but
no, random,
I mean,
because in our data set is 25% bias. So I think if it's
let's say balance 0.43, this is my question is more like where the difficulty is coming from, right? Did you analyze the structure of the error? So where the issues are coming? Because if you were using these basically embeddings, right? You are far from semantics, really, right? You don't really understand the message. You are just more like, it's more like a keyword search. So it's not, so my question would be, wouldn't it be better to maybe try to go a little bit deeper into semantics with LLMs now you can do, right? So I don't know, 3 years ago, this was impossible. Today you can do these kind of things. So could you comment a little bit on structure of the error and how to improve these numbers? Right?
Okay, great. Yeah, thank you very much for the question. So basically, the first thing I would like to mention is here, those strategies is we just use really preliminary search, like this need to be further studied. Second is, as you can see, we check our result. And then, as you can see here, we basically distinguish terms into 3 categories. And in the final result, we found that all in a sentence that contains the terms from the prohibited category, we got them all correctly. And in the second category, conditionally biased, is also have really high precision. The difficult part is in the context sentence terms, because it largely depends on the context that maybe actually is the most difficult part. And that will be the next job in our future. Yeah, really, almost it's 100%.
I don't understand why the first sentence is actually prohibited. I mean, what makes it so biased that it's prohibited? I mean, it seems like to me just a normal fact. I mean,
I think there's two things. And the first thing is we basically use the handicap to label the group of people. And second thing is now we translate it into English. Maybe in the original Dutch word, sometimes it actually contains more bias.
Okay, thank you. Let's, due to the time limit, probably we have to do offline discussion, and then let's, well, thanks our speaker again. So we will proceed to this online presentation or this is just a video. This. The former one. This is a little bit from this one. Okay, so our next speaker is going to present the work, how much medical knowledge do LLM have? So please welcome our. And how to okay.
Hello, everyone. I'm here to present the work titled How Much Medical Knowledge Do LLMs Have? An evaluation of medical knowledge coverage for LLMs. This work is completed by the Jarvis Research Center, Tencent U2 Lab, Shenzhen, China. As LLMs has become increasingly integrated into real-world clinical environments, it's crucial to conduct systematic and rigorous evaluations to ensure their effectiveness and reliability before their deployment. To evaluate LLMs in the healthcare domain, several traditional evaluation frameworks have emerged, including PromptCBlue, MedBench, and MedJourney. These frameworks provide insights into the capabilities of LLMs in answering medical questions and assisting medical professionals. However, they exhibit significant limitations, especially for the measurement of depth and breadth of medical knowledge that LLMs possess. That's because they are mostly task-oriented or scenario-oriented. Therefore, they do not provide a reliable means to quantify the exact amount of medical knowledge within the evaluated LLMs. This raises an important question that has not been answered. That is, how much medical knowledge do these LLMs actually have? To this end, we propose MedKG-EVO, a systematic framework designed to conduct both task-oriented and knowledge-oriented evaluations for LLMs based on medical KGs. We design a range of tasks in our framework to benchmark LLMs understanding of different levels of knowledge within the medical KGs. Those examples are illustrated in this figure. Specifically, we construct 3 different levels of tasks, including first, entity-level tasks aim to evaluate the understanding of medical entities and concepts. Next, relation-level tasks aim to assess the differentiation of medical relations. Last, subgraph level tasks aim to evaluate structural understanding and reasoning. In the three main tasks, 9 subtasks are listed in the following table. We consider 2 types of questions in MedKG-EVO, that is true or false questions and multi-choice questions, that is TFQ and MCQ for short. For entity level tasks, we design entity typing, entity clustering, and entity disambiguation. Next, for relation level tasks, we design relation typing, factor check, and relation prediction. And for subgraph level tasks, we design 3 subtasks called error recognition, reasoning as TFQ, and as MCQ. For the task-oriented evaluation, MedKG-EVO uses accuracy as the metric. Besides this, MedKG-EVO introduces a novel knowledge-oriented evaluation approach that integrates all tasks to comprehensively assess the overall coverage of entities, relations, and triples within a medical KG to make the evaluation. To quantitatively measure their knowledge coverage on entities, relations, and triples, we propose a new metric termed coverage. The coverage average E and the coverage average R are straightforward measurements of the overall performance. We further introduce the degree-aware coverage, that is coverage degree E and coverage degree R. This metric emphasizes the varying importance of different entities by giving more weight to those with higher degrees. Similarly, the triple coverage T, is also proposed to measure the overall knowledge coverage on the medical KG about the triples. For the environmental setup, we choose CPUB MedKG and SAMGPT as the baseline KGs, and we downsample them to facilitate the experiments. For the choice of LLMs, we choose 3 types of them. First, 5 open source LLMs with different scales, including Qianwen-2 and Baichuan-2. Second, 5 medical domain specialized LLMs, including DiskMed LLM, Huatu GPT-2, House, and WinGPT. And last, we also include the closed source LLM GPT-4o. This table presents the task-oriented evaluation results. On the benchmarks derived from CPUB MedKG small, GPT-4o outperforms the other LLMs, followed by Qianwen-2 and WinGPT-2. When examining performance across different levels, most LLMs excel in entity-level tasks and show relatively lower performances in relation-level and subgraph-level tasks. We also find that as the number of parameters in LLMs with the same architecture increases, the average accuracy also improves. We also observe that the general domain LLMs often outperform their medical domain counterparts. This surprising finding may be due to the data utilized during the fine-tune phase, which is more focused on specific tasks rather than on acquiring medical knowledge. The next table presents the knowledge-oriented evaluation results for each LLM. Overall, GPT-4o still demonstrates the highest coverage of both entities and relations, followed by Tianwen 2. We experimentally find that larger scale LLMs tend to have a greater capacity of knowledge retention. When examining coverage average R and the coverage degree R, we observe that coverage degree R is always greater than coverage average R. This indicates that when a relation appears frequently in a medical KG, it is typically well presented in the pre-training corpora. And thus, LLMs demonstrate a better understanding of this kind of relations. We select 4 example LLMs and show the accuracy of all the questions related to one entity. As illustrated in this figure, we can easily compare the varying levels of understandings. For example, when we analyze the common disease, diabetes, GPT-4o again leads in the number of correct answers, followed closely by Tianwen 2, WinGPT 2, and by Tran 2. The findings indicate that MediKG Evo serves as an effective tool for pinpointing specific areas of medical knowledge where certain LLMs may exhibit differences and thus enhance the effect of LLM fine-tuning. For the relation knowledge, we can find similar patterns. For instance, by Tran 2 struggles with the relation called related transformational. To improve accuracy, it would be beneficial to incorporate additional data related to transformational relationships in the next round of the fine-tuning of by Tran 2. We have open sourced our code scripts and the benchmarks at this GitHub link. We are also actively expanding our analysis in different LLMs, including DeepSeek V3, DeepSeek R1, and etc. Please stay tuned for additional results to be released soon. Thank you for your attention.
Thanks for the talk. Do we have any questions from audience?
Hi, thanks for presentation. Could you please elaborate a little bit on the difference of the 3 levels of benchmarks you were using? Maybe give some examples. I mean, I think it's quite pretty clear what's their entity one, the very first, the easy one, but then the second and the third, if you could give few examples of what kind of questions were asked and yeah, the correct answers and the wrong answers will be good to understand. Thanks.
Sorry, could you please repeat the first question?
That's one question only. What's the difference between different types of benchmarks, questions, the LLMs were tested against? You have 3 types, right? The entity level, and then there's 2 more. So what's the key difference between them?
Okay, let's see their example illustration to see their main differences. So in the we can see in medical KGs, there are the points of entities and the edges of relationships, and the two points with edge with an edge to make a triple. So in the right of subgraph, we can see the examples of this subtasks. For example, for the entity disambiguation, it analyzes whether a point that is an entity is exactly the same as to another point that is another entity. And for the second relation level tasks, we can see that it analyzes the edges between the points. And for the subgraph level tasks, it's mainly considered the structural relationships between the edges and points. So they examine the different level of views in the medical KG. Can you understand that? Thank you. Yes.
Let's let our speaker again. Due to the limit, we will proceed to the last one. So I guess the last one will be online presentation. Do we have the speaker for this one? If not, I guess it will be online presentation.
Adaptation. So this work addresses the growing challenge of accurately identifying at-risk individuals. Use from user to visit.
Why?
External platforms such as
I already turned it off. On? You mean this off? Let's see. There's no sound will be. There's no sound. You have to turn it on. Okay. Ready? Use my. Let me do this one.
Hello everyone, I'm Swansea and
Could you please try to share the sound?
Today I'll be presenting our work on distorted grading approach for human-assisted online suicide ideation detection. So this work addresses the growing challenge of accurately identifying at-risk individuals from user-generated text on platforms such as Reddit or Twitter X, where ambiguous, noisy, inconsistent, content makes risk detection difficult. So suicide remains a global crisis, claiming over 900,000 lives each year. Social media has become an important platform where individuals dealing with suicide ideation express their distress. Studies have shown that individuals often share their mental health struggles online rather than seeking help directly. This creates an opportunity for early detection of risk and enabling timely interventions. Detecting suicide risk from user-generated content presents significant challenges, such as ambiguity is a key issue. Individuals often express their feelings in direct or unclear ways. Additionally, noisy nature of social media language, ranging from slang to misspellings, adds complexity. Furthermore, false positive, flagging harmless content, or false negative, such as missing real risk, pose critical concerns, especially when lives are at stake. Current systems often fail to handle these complexities. So current methods for detecting suicide ideation in online posts face several gaps. For example, traditional models often fail to capture the nuanced context of informal social media content. Furthermore, these models do not prioritize cases that require human review, which could lead to missed high-risk cases. Deep learning approaches also suffer from inconsistent performance, especially in case of uncertainty, resulting in poor decision-making. What's significant in current systems is the limited integration of human expertise. While AI can assist in detection, experts are still needed to provide the nuanced judgments in uncertain cases. Additionally, current models do not have a system for prioritizing high-risk cases for expert review, which is important for timely intervention. Lastly, many models fail to handle uncertainty. There is no mechanism to abstain from predictions when the model is not confident, leading to potential errors. Right, now let's move on to our key contributions. First, we introduce a model that uses deep learning to detect suicide risk with a focus of self-awareness. One unique feature of our model is that it refrains from making a prediction when a model is uncertain and avoiding risky predictions. Second, our model selectively prioritizes high-risk cases to ensure that resources are focused where they are needed the most. Finally, our model shows improved failure to self-reject FSR performance compared to previous models. We'll see how it performs both traditional and state-of-the-art models like SASI and Mentalbot, which I'll talk about later on. So our proposed model introduces a novel approach by incorporating selective prioritization. It not only makes predictions, but also decides when to defer to human experts, reducing the workload for professionals. This system exhibits self-awareness, abstaining from making predictions when it faces high uncertainty. Through quantitative evaluations, we show that our model avoids incorrect predictions in 83% of high-risk cases, which provides a more reliable decision-making tool for mental health professionals. Now, let's move on to our key contributions. First, we introduce a model that uses a deep learning model with a focus of self-awareness. One unique feature of our model is that it refrains from making a prediction when the model is uncertain and avoiding risky predictions. Second, it selects and prioritizes the high-risk cases to ensure that resources are focused where they are needed the most. Finally, our model shows an improvement performance compared to the previous models. Our model introduces an approach to human-assisted classification. Unlike prior models that rely on arbitrary thresholds, we use a distorted greedy algorithm that comes with strong theoretical qualities. Our model integrates three core components: deep representation learner, a suicide ideated classifier, and a novel multi-classified abstain mechanism to decide which predictions need human oversight. Let's look into more details of our method. So each user host is encoded with a word model with a 768 dimensional feature vector. These features are then passed to a STM with attention layer to predict suicide ideation. We call this same model as IM. However, instead of relying solely on this classifier, we train 10 diverse classifier, each outputting the predictions with associated confidence scores. If the model is not confident, through it abstains and then sends the sample for human review, minimizing the unnecessary human effort. At its core, our proposed model is a distorted greedy model, which balances between maximizing prediction accuracy and minimizing the cost of the human source. We model this function where G captures the gains from the prediction accuracy and B represents the fixed cost of the samples to human. Using distorted greedy algorithm, we select the most informative samples for human review. And this is optimized using a special loss function called Gambler loss that ensures that both classifier and abstain function are jointly trained in a consistent space. So the key objective of proposed model is to optimize the trade-off between classification accuracy and outsourcing cost. We use a weekly submodular function to ensure we can approximate the optimal solution effectively. The loss function guides the model to focus on uncertain samples and minimize the human living cost. We select samples iteratively, ensuring that human experts are used only for the most uncertain cases. To summarize, post model moves beyond that hoc selection rules by introducing a fully theoretical and practical model for human value classification. The combination of representation learning, multiple classifiers, and principal abstaining ensures that the human experts' time is spent only where the model is generally unsure. In experiment, we found that post model significantly outperforms previous models while reducing the reliance on the human labeling. We evaluated our model against multiple baselines, both traditional and deep learning recent SOTA models. For traditional, we use SVM, Brenner Forest, and MLP, where the deep learning models consider architectures like CNN, LSTMs, word-based models, and then some recent methods such as Mendelberg and SAMGPT, especially designed in a suicide to abstain the failure cases. For evaluation, we use F-score, failure to safe reject, which quantifies how often the model avoids making prediction when it is unsure or uncertain. And for the data set, we used instances of 500 users who were assigned to one of the 5 suicide risks based on their engagement with 9 mental health related subreddits, which are labeled by the 4 practicing psychiatrists using Columbia suicide severity rating criteria. And that this dataset had 5 labels, represents an increasing severity risk, and the distribution of these tables is shown in this table on your right hand side. So now let's look into some of the results. So from these results, we can see that our proposed model consistently outperform traditional models and achieve significantly higher F-score values across various thresholds. And in particular, proposed model achieves 0.81 performance at 50% coverage and 0.69 at 85, and performs well even at 100% coverage. When compared to deep learning models like CNN and STM, proposed model outperforms them in terms of both F-score and fail to safe reject ratio. And we also observed that SASI, which is a previous order model, while effective at times, produces more false positives at higher threshold when making it, which makes it more or less reliable. So we also looked into the sensitive analysis. So we performed sensitive analysis to understand the relationship between coverage and F-score. So proposed model achieves perfect FSR at the coverage levels, ensure that no false positives are made. As we increase coverage from 10 to 100%, we see that F-score stabilizes around 50 to 70, suggesting the diminishing returns at higher threshold. This indicates that proposed model can operate efficiently with relatively low coverage, maintaining high performance while limiting resource usage compared to the previous SOTA model SASE. In our regression study, we systematically evaluate the contribution of different components of a proposed model. The baseline suicide ideation model same performs reasonably well with an F-score of 0.53 but when we add calendar loss, the performance improves to 0.60. That shows that the performance of controlling decision uncertainty. However, the full model, which is distorted reading abstention function, achieves an F-score of 0.81 at 50%, highlighting the importance of abstain mechanism in improving performance. So now let's look into some of the qualitative analysis. So here an example for our qualitative analysis. Consider the user C, where the post indicates a high risk of suicide. Post model correctly flags this post. In case where the model is uncertain, the proposed model abstains from making a prediction that shows and ensures that there is no false harm. Additionally, post model prioritization mechanism ensures that high risk posts are flagged first for human review, which allows timely intervention. So now let's talk about some real-world scenarios, applications of our proposed model to assist the mental health professionals. Our proposed model can have to flag the high priority posts that require immediate human review. It can also help categorize posts based on the risk level, high, medium, and low, to ensure that high-risk individuals are detected early and appropriately categorized. It can also help with the early and accurate detection, which enables prompt interventions. So in short, proposed model does not just detect risk, it integrates into a system that provides real-time actionable insights to mental health professionals supporting timely interventions. In conclusion, the proposed model introduced highly effective and novel approach to suicide risk detection by integrating selective prioritization. By incorporating intrinsic self-awareness, proposed model can refrain from making predictions in uncertain situations that ensures only the most accurate and reliable risk assessments are made. This self-awareness mechanism allows us to minimize the risk of false positives, and our qualitative evaluation shows that proposed model avoided high-risk situations in 83% of the cases by abstaining from incorrect predictions. In future, we aim to expand the deployment of proposed model across a broader range of online health communities and also enhance its multilingual capabilities to ensure its use globally. And finally, we envision to develop a system that enables continuous monitoring and adaptive learning, allow proposed model to improve over time as new data and trends emerge. Thank you very much for your attention. I'm happy to take any question or discuss our work further. If you would like to follow up, here's my contact information. Feel free to reach out. Sorry, due to some teaching commitments, unable to attend in person. But if you have any questions, I'm happy to answer online or via email. Thank you very much.
Okay, thank you for the presentation.
Hello everyone, I'm Swansea, and today I'll be presenting our.
Sorry. Okay, so I guess the speaker is not online, right? So that's the end of our session for today. And then thank you very much for your attendance. Thank you.